SMA 205 Video AI, we're going to talk about exponential growth. So this is some kind of quantity that grows or can decay at a rate proportional to its size. So I'm going to start off with this example problem, and this is a cow loan problem. So you're investing your cow loan, a quantity of $35,000, into a local CD, but you forgot the interest rate. So 1 year later, you check the balance and you notice that it's $36,610.98. So the question is, how much money will you have after 5 years? And assuming monthly compounding interest, what is the interest rate? So the first thing you have to do is define your variables. So in this case, we're dealing with money, so we'll call it M of t, and that'll just be the amount of money at any time. In this case, we'll say time is in months. And we have an initial condition. So time 0, we had $35,000. And we have a second initial condition. At 1 year, or 12 months, since we're dealing in monthly compounding, we had 36,610.98. Okay, so some of the assumptions that we have to follow is we have unlimited growth. Or in this case, unlimited money supply. Okay, and since we're dealing with a bank, we have to assume the bank won't go out of business. Okay, so now to model this differential equation, it's a quantity that grows or decays at a rate proportional to the size. Okay, so we want to have modeled the growth of money over time, and proportional means k, or a proportionality constant, proportional to its size. And the size is whatever the current size is, m. Okay, and that m is really this amount of money at any given time. Okay, so I can solve this differential equation using separation of variables, in which case bring the m over to the left side, leave the k and the dt on the right side. Okay, I'm going to integrate both sides, in which case I'll get the natural log of m equals kt plus c. Okay, so I want to solve for m, which is really a function of time. Okay, so I'm going to raise both sides to the e, in which case this e to the t can be broken up into e to the kt times e to the c. Okay, and this is my general solution. Okay, so I want to apply initial condition to solve for this constant of integration, and that's going to be my initial 35,000. So at time 0, I have 35,000. And that's e to the k times 0. I'm putting a 0 in for time, times e to the c. This term goes to 1, therefore e to the c is 35,000. Okay, so now I can write my particular solution. M of t is going to be 35,000 e to the kt. Okay. There's one thing missing in my particular solution, and that's this proportionality constant. Okay, so I'm not sure what that proportionality constant is, so I'm going to apply my second initial condition and actually solve for what that proportionality constant is going to be. Okay, so I know at time 12 I had 36,610. Okay, so what I'm going to do is I'm going to set this value, 36,610.98, is equal to 35,000 e to the k times 12. Okay, so this represents at time 12 I have $36,000. Okay, so now I want to algebraically solve for that k value. So this will be 36,610.98 divided by 35,000, and then to cancel the e, I'll take the natural log of both sides and then divide by 12. And this gives me my k value, in which case k is going to equal 0.00375. Okay, so now my particular solution is complete with a k, 75t. Okay, so this I've now solved for an equation that will model the amount of money at any given time. So I can answer my first question, how much money will I have after 5 years? Okay, in which case that is just m of 60, where 60 months is 5 years. And this comes out to be $43,831.30. Now we're ready to determine the interest rate. Okay, so the interest rate is really how fast something is growing. So this grows at a rate proportional to the size. Okay, so what determines how fast our money grows is this k value. Okay, so this k value is really our interest rate, in which case we had 0.00375. Okay, but that k value represents a monthly interest rate. So if I just multiply it by 12, then I get 0.045, or a 4.5% interest rate. Okay, but that doesn't seem exactly right if I do one additional calculation. If I determine how much money did I make in that 1 year. So if I take this 36,610.98 and subtract the initial amount, okay? So in the numerator I have the money earned over the first year, and I divide it by my principal. Okay, then this comes out to 0.046, or a 4.6%. Okay, and this is called I actual. Okay, so this is the term that you'll see advertised by the banks. Okay, and that's assuming that you reinvest your monthly dividends. But this is the actual interest rate that you're earning every month. Kept in for a full year, you will make 4.6. Okay, one additional thing we can do with this differential equation is determine how much money am I making every month. Okay, so if I take dm dt, and I just want to know how much money I make in that very first month. I know the k value is 0.00375, and that very first month I'll have just the 35,000. Okay, and this will come out to 131.25. Okay, so in that very first month I'm going to make an additional 131.25. If I want to figure out how much money I'll make in my last month, I'll say dm dt is the same 0.00375, and in my last month I had 43,000, so I'll put that here, 43,831.3. And this tells me if I go to the next month, the 61st month, I'll make $164.36. Okay, so this is the rate of change of money, the change in money over time. So if 1 unit of time is a month, that's how much I'll make in one given month. Okay, so to confirm our work, we'll model this using Euler's method in Excel. So if I have a step size of 1, which is in this case months, okay, this again is a large step size, so my answer won't be very accurate, but it'll work for this model, be very close. So my initial condition was 35,000, and if I follow this down to 60 months, I'll have $43,812. And again, that's not exact. Our exact answer was $43,831, But again, if I reduce the step size and go out more iterations, I'll get very close to the exact answer as well. Okay, and you see this is how much money I'm making in that very first month, the $131.25. And in the last month, I'll be making $164.30. And visually, you see that the money will grow exponentially, okay, as long as the bank stays in business and there's an infinite supply of money. You see it grows without a restriction. And at the end of 50 years, or 600 months, you should have somewhere around $325,000 from that initial $35,000 investment.